is my presentation on my paper, Emergence of Recursive Language through Bootstrapping and Iterated Learning. So I'll be the outline for the presentation is first I'll discuss my research objective, then I'll move on to background, then I'll discuss the experiment and results for the paper. So we'll start with some definitions. First is human language. What is a language? So language is a structured communication. It's such a system of communication that consists of grammar and vocabulary, and it is a primary means by which humans convey meaning. Maybe like how do we talk? Uh, so we, as human, we have a structured way of structured method of uh, structured method through which we communicate with other people. So there's a predefined language that exists in our society, and we use that to communicate to the other people. So that we say is a language. Then what is recursive language? So recursive language is a fundamental linguistic feature that allows for the generation of infinitely complex expressions from the finite set of rules. So there will be limited set of rules will be there in the language, and then we use them recursively to form a larger sentence or complex sentence from a set of sentence. So in that way, we can use a recursion or recursive language, which we can create a sentence or phrase which have a high complexity or with a variable complexity with the repetitive structure generated by the grammatical mechanism. So if we take an example, uh, uh, like in a sentence, the man who sold the house that Jack built will move to the city. So if we see that there are multiple levels of recursions here. So if you see the sentence, uh, the man will move to the city, and then we had a recursion in between that who sold the house, and then another recursion that Jack built. So we have multiple levels of recursions here. This is called multiple levels of thing. So it keeps adding meaning to the sentence. Now we'll discuss the iterated learning. So iterated learning is a framework used to study the emergent language structure by simulating the cultural evolution. So if we have to explain iterated learning, it's an inductive process where one individual develops a behavior or a characteristic by the realization of how the other people or the individual before it uh, when he acquired like the way he acquired that knowledge, a similar way the other next person will acquire the knowledge. So it's a kind of transmission or the cultural evolution, like how things are transmitted from one generation to the next generation. So iterative learning is a framework through the people learn or the anyone learn from their previous generation, and they in turn learn from their previous generation. So that is an iterated learning that we use to study the cultural evolution or the any emergent properties that happen through the cultural evolution. Now, what is the research objective? So in this our paper, we study the language acquisition and the emergence of groundedness and the recursive linguistic structure in a neural through neural iterated learning. So our goal will be to study whether the language can be grounded and whether the recursive linguistic structure can also emerge in a communication. And we'll also see the language acquisition. So how the successive generation learn from their previous generations. So this is like the way we do is we have a goal which requires the multiple levels of communications. So then we have to use the recursion or the recursive language to convey the communication or to convey a goal which requires the multiple level of communications. Then we model this process as a language game. This is a standard way of doing uh, in this research area. So we develop this process as a language game within a framework of decentralized multi-agent deep reinforcement learning setting. So, what is language games? The language is a kind of framework or the embedded in a cooperative society in which communication is useful. So if we have to say it's a computational language model where society kind of society is there, which are used to study the language, study the communications, or study the emergent patterns from the these games. So what happens in language game is there will be a common goal for the agents, and then they have to achieve that, or they have to complete the goal by learning to cooperate using the communications. How to model this problem? So we use three things as we discussed earlier. The language games is crucial. Then we formalize the setting using multi-agent Markov game, and then for learning the or getting the success, we use multi-agent, or training the objective, we use multi-agent reinforcement learning. What is a multi-agent Markov game? Markov game is a tuple which consists of state, the finite sets of players or the agent, and then each agent has a denotes the each agent's action, right? And then R denotes the reward, which is for every player that given the state and the action he took, if we have a reward, and P is the probability transition. Uh, so given a state and the action taken, what is the next state we move on? Gamma is the discount factor, and mu is the additional information that is available to the specific player. Then comes the Markovian objective. How do we optimize the problem? So in the if you see in the language game agent, how do we uh, maximize the reward, or how do the agent achieve the goal? So here the collective goal of the agent population is to seek a policy or that maximize the global average return, long term return over the network based solely on the local information. So basically, every agent has to maximize maximize the reward in turn to get a uh, optimal policies. Then there's one definition called emergent vocabulary. So in emergent vocabulary, what how we define is that is a shared mapping, or that is a mapping between the concept uh, and the vocabulary. So for the lexis, there is a function between the lexis and the concept space. And so suppose there will be C concepts are there, uh, and the psi concepts are there. So total number of vocabulary possible is C to the power y psi, and then into form of forming a common vocabulary, they have to agree on a specific vocabulary to converge into a some coordination and consensus. Now we define our language game. So we will describe our language game, the what kind of language game setup we took. So in our language game is a simple connected graph. Uh, it's a bounded 2D plane where we are the set of vertices and the edges, and all the vertices are similar in shape and but have a unique location. And to each to each vertex we assign a unique color, or predefined, like from a predefined set of colors we assign one color to each vertices. So this is kind of language game setup. So what happens in a language game? Like what is the how do the language game proceed? So in a language game, speaker agent there will be uh, agents will be assigned a role. One will be speaker and other will be listener. The speaker agent chooses a target node, and then it will try to communicate the target node to the listener by presenting the utterance symbol. So it has to utter a word to convey this to the listener. And the objective of the listener will be to decipher the meaning of the utterance and identify the target node. And thus, like if the utterance is accepted, we say they have consensus on the word word and the concept mapping. So this interaction is subsequently rewarded according to the interpretation outcome. Uh, that is a that is shared among the participating agents. Here, that is speaker and the listener. So initially there will be no predefined mapping attached to the utterance symbol. So when the initial start of the game, there will be no meaning attached to the utterance symbol, and then through the uh, continuous trial and language play, these agent will start to agree on the one common language or mapping of the utterance symbol. So that's how they learn to communicate and agree upon a single language. So that's what it makes the problem little difficult because there is no predefined meaning to any utterance symbol, and they have to learn on their own uh, to communicate the target node or the goal. So we come to the space conceptualization. So similar to the humans using the cardinal direction, here agents also use some kind of uh, the way to conceptualize the space. Here, like we define them as the sector segments and the colors. So each, depending on the speaker's location, it divides the space into the segments, which are the circular rings, and the sector is the quadrant kinds of division of the 2D space. So, given any node, we can conceptualize. Given suppose any target node is there, any node is there, we can conceptualize it in a tuple of segment, sector, and the color. So that can be any topic node is there. Agent can have the concept of that vertex that is related to the current location of the agent. So suppose speaker is speaker is standing here, and then it will conceptualize the whole space, and then it can find the concepts of corresponding concepts of any target no. Uh, so what is the spatial concept space here? So as we discussed earlier, the concept space is the union of the segment, sector, and the color, and the null concepts. Null concepts means like it does not utter anything, or it does not choose uh, to convey that any concept which is not required, or which like no speaker think that that is not required or sufficient, not required for the communication, and the rest of the concepts are enough to convey the target node. So so if you see sector one is 0 to pi, this one sector is 0 pi, and sector 2 is pi to 2 pi, or sector 3 will be 0 to pi, the other half. So, and the left quadrant. So if the speaker thinks that the vertex can be used in this quadrant, sorry, this half semicircle, it will try to take the sector one. Otherwise, if it thinks that it needs more conceptualization, it can put sector 4 or sector 3. Unless segments are the circular rings, which it can choose to conceptualize the space. Now, what is the overall semiotic cycle of the language? So, I'll quickly explain this. So, suppose any target node is there, speaker is there, the speaker will conceptualize the space. Then it will be converted into this, the corresponding concepts will be taken, and then it will be uh, we'll have a we'll have a embedding for that concepts, and then a vocabulary will be uttered by the speaker. Uh, then the, the speaker's vocabulary will be interpreted by the listener, and then the corresponding concept will be the listener will try to decipher the meaning, uh, decipher the concepts from the utterance, and then the prediction. Then according to the we check that whether they are the same concepts that were predicted that were uttered by the listener or not. So that is how the whole semantic cycle of the language game is. This is the policy architecture that we use in our the language game setup. So we'll use two concepts. To have the embeddings, we use the DNN network, uh, and then we use the LSTM network to have a continuous utterance for the concepts. And then after the concepts uh, there will be a discrete communication channel between the speaker and the listener. These words will be taken by the listener, and the listener will try to decipher it, and it will predict the vertex. If you see, the listener also has the listening module, the speaker has also the listening module, and the listener has the speaking module. This is updated internally so that the next time when they switches the role, the opposite mapping is also preserved. So that is similar to the way humans have. If we learn to speak, we learn. If we learn to understand any meaning, we learn to speak also. So that is this is done to have the reverse mapping also, to learn the reverse mapping also. So each agent is decentralized here, and the communication success is only guided. So if you see that both the agents are decentralized, and there is no back propagation possible between these two agents, and the communication success is only guided through the shared reward. So there is no telepathy between the agents. So there is no back propagation, or they cannot read the minds. If we say simply. Next is recursive communication. Initially we discussed what is a recursive communication. So we discussed the setup of this recursive communication. So we saw that the goal, the speaker has to convey the goal vertex. But in recursive communication, suppose this goal vertex is that it cannot be conceptualized directly or unambiguously. It will go through some path. So instead of directly uttering the concept for this word, it will take an intermediate vertex, and then from that intermediate vertex as a source, it will add the final vertex. So this is the kind of recursiveness we are trying to bring in our setup. So speaker and listener can have the communication in a way which have the multiple levels of interaction through recursion. So this is our objective function. So we have uh, three loss function or three objectives in the loss function. First one is regularized cumulative reward. That is the shared reward is maximized. The concept selection loss. So speaker chooses the and the appropriate and only the required number of the concepts. We use this loss. So it does not use any the concepts which are not required or not necessary. And the third one is interchangeability loss that we discussed to get the reverse to learn the reverse mapping also. So we use the interchangeability loss. This is the reward function. So in the reward function, if GT, the predicted vertex and the goal vertex are same, we give the full reward. Otherwise, we give the partial rewards. And now we come to the results. So this is the success ratio and the reward maximization. So if we see that success ratio, the success ratio gradually goes to the close to one. And these dips, if we can see, these dips account for the role switching of the agent. So when the role switches, there is some little bit of fluctuation, then it again rise to the same success ratio. Similar for the reward also, there are some drops because of the role switching between the agents. And then there is a convergence of individual loss plot. So we show that no every loss, every component of the loss objective function we discussed, it has stabilized around the zero. And this we say the consolidation of symbols. So agent one and agent two, if we took as a speaker and a listener, like we switched the role also. So initially there were no mapping or no fixed prominent mapping for the vocabulary and the concepts in this concept, but around epoch 12,000, the mappings became the consist prominent. If you see that there's a prominent mapping and they are matching also, so they have emerged at the language emerged a common language. And then as we discussed the iterated learning, the next generation comes and they have to learn from the previous generation. So this is called a recursive structure that propagated in the successive generation. So we say that agent three and agent four, that agent came around. They also learned kind of almost not exactly, but similar kind of vocabulary mapping. So they were introduced at one at 5,000 and one at 10,000, and each of 10,000, they both are stabilized. So in the conclusion, I would like to conclude this. I would say that we demonstrated this. the emergence of grounded recursive language with the depth one. So then there was only we tried with the one intermediate vertex when grounded machines are communicated by breaking them into the comprehensible parts. And then we observed how agents learn to consistently use a common symbol for identical concepts within the message. So to have a language, they have to to they have to use the same symbol for the same concepts. That's how the language forms. And then our finding underscores the enduring nature of recursive structure, indicating their transmission across the generation and communicators, and emphasizing their fundamental role in shaping effective communication dynamics over time. So, thank you. This is my presentation.